the weekly assignment is due Monday, not today. And today I'm just going to do 2 example problems that I think will help with that. I'm going to do 2 3D problems. And here are the 2 that I'm going to do. They're both going to involve a plate. On a second. Those are paste. How do I copy? Okay, so it's going to be the same plate, but one of them is going to be with just a single hinge joint at the corner, and then connected to the wall by a cable. And the other one is going to have pin joints at both corners. With that same cable connecting it. Okay, so that's.
So I have a quick question.
Yeah.
If there's thrust on a hinge, I guess maybe I'll answer this later, but like the only way for there to be thrust on a hinge is if it's like clasped by 2 different things holding it together, like holding the hinge in place, right? Like there doesn't add thrust to have newtons pushing up on the door. Like after the
Right. There has to, I mean, it has to be a mechanism inside the joint. But like if you think of a hinge like on that door, it looks sort of like this, but it does have little brackets that keep it from moving up and down.
Yeah.
So, but any time I give you a pin joint or a hinge joint, I'll tell you whether there's thrust.
Okay.
So
there's no thrust in the.
in in the weekly assignment, or let me look at it. Oh, I remember it. There is not, but that's just because of the way the other forces are acting. You'll see that you would calculate a thrust of 0 anyway, so it doesn't even matter. And let's change one thing about this actually now that I'm looking at it. Let's change it so that the cable connects like that. Okay, so I'm going to start with just the single pin joint, and there's a cable that goes from the middle of the front up to this point here. The width of this is 0.5 meters. The length is 1 meter. and the height of that connection is 0.3 meters. And then it's connected to the wall by a pin joint. And that joint is a pin with thrust. Oh, and we need a mass. Let's say the mass of this plate is 30 kilograms. All right. So we'll start with a free body diagram. There's a weight force acting from the center. That's 30 times 9.81, so 294.3. There's a cable force. I'll call it T. And the only other place that there is contact with this body is at the pin joint. And we're treating that like it's right in the corner. I didn't give any distance from the corner or anything. So this is a pin joint with thrust, and there's no other pin joint sharing its axis. Yes. Thrust is a force along the axis of rotation of the pin joint. And so, so this is going to have a force this way. I guess I'm choosing the directions of let's call this the x-axis, y-axis, and z-axis. I'm going to move this a little away so I can, come on. Okay. So those are the forces, and I'll call those R. And then there are also two couples if you don't have another pin joint sharing the axis. So which two axes have couples? Well, we know that there's no couple around the axis of rotation because it's free to rotate. So the two have to be this way, and I'll call that M, Y, and then this way, and I'll call that MX. Any questions about that treatment of the joint? And now I'm going to go through my table values. So rho F moment.
But how do we know it's not like M, Y, and Z? Is it always going to be M, Y, and X?
No, it just depends how you choose your coordinate system. I'm going to choose my coordinate system with X this way, Y this way, and Z this way.
So I can't go into the wall, so that why it's not going that way.
Is that why what's not going?
Is
What?
that why MZ isn't a thing? So it can't go into the wall?
No, MZ, remember that those couples are only there to eliminate rotations, to eliminate rotational degrees of freedom. So if you had a couple pointing along this axis, that wouldn't allow rotation about the axis. Okay, so this one says that that this end can't turn up. This one says that the thing can't rotate around like a frisbee. Yes?
Basically, because it can rotate around the y-axis, but because we're in statics, we know it's not. There are no forces there.
This z-axis?
Yes, Z, not
Right. It can, like, if the only thing acting on it was that hinge, it would be free to flop up and down, and so there's no couple there. Okay, so I'm going to put my about point here. And I'll start with the force R. The row vector is 0, 0, 0. The force vector is Rx, Ry, Rz. Cross product is 0. Then I'll do the couple at that joint. I'll call it M. For couples, you don't care about this stuff. There is only an MX and an MY. Then we'll go to the weight. The row vector, so to get from the about point to where the force is applied, you go 0.5 meter in the positive X direction, 0 in the Y direction, and 0.25 meters in the negative Z direction. And the force vector is in the negative Y, so 0, negative 294.3, 0. And, oh, I left my stuff in the stupid other room. So the cross product, okay, so do this cross product by hand. For the X moment, it's 0 times 0 minus this times this, 0.25 of 294 point, oh God, I can't do that in my head. Can I just borrow someone's calculator for this? Anyone have a calculator? Thank you. Let's see, what do you got here? Inspire, yay. Okay, so.
Should be charged.
Yep. So we got 0.5, 0, negative 0.25 crossed with 0, negative 294.3, 0, and the cross product is negative 73.575, 0, negative 147.15. And then the last force, or the last load that we need, is that cable force. And so we have to think about that. So I'm going to think about that about point as the origin. And so a vector that is in the direction of that cable force is going to be the coordinates of where it attaches minus the coordinate of where it attaches to the body. So where it attaches to the wall, if the red dot is my origin, would be 0x, 0.3y, and negative 0.5z. Come on. So 0x, 0.3y, negative 0.5z. And then we're going to subtract the coordinates of that location, which are 1x, 0y, and negative 0.25z. So a vector in the right direction is -1, positive 0.3, negative 0.25. And so the unit vector is negative 0.931, positive 0.279, and negative 0.233. And so the cable force is just going to be this times T. So, the row vector is just going to be the coordinates of that location, with this as the origin. So that is 1, 0, negative 0.25. The force is negative 0.931 T, positive 0.279 T, negative 0.233 T. Now the cross product is 0.070 T, 0.466 T, and 0.279 T. Okay, any questions on that one? And now I'll go Newton's second law. Says Rx, Ry, Rz plus 0, negative 294.30 plus negative 0.931 T, 0.279 T, negative 0.233 T is equal to zeros. And the moment equation says mx, my, 0 plus negative 73.575 0, negative 147.15 plus 0.070 T, 0.466 T, 0.279 T, is equal to zeros. And now we can go to the augmented matrix. So how many equations and how many variables do we have? None of these go away as 0 equals 0. So we have 6 equations. So we better have 6 variables also. And we have, well, really, if you have more equations than variables, if you're lucky, you can just drop an equation of your choice and it'll work fine. Really, the problem is if you have more variables than you have equations. We have 1, 2, 3 for the R's, 4 for the T's, 5, 6 for the couple components. So it looks like we have 6 and 6. This should work. So here's our equations. 1, 2, 3. Did I only do 5? 1, 2, 3, 4. 4, 5, 6. Okay, and for the equation, for the variables, I'll go Rx, Ry, Rz, Mx, My, T, and then the constants. And equation 1 says Rx's, we have 1. T's, we have negative 0.931. Everything else is 0. Equation 2, Ry's, we have 1. T's, we have positive 0.279. Constants, we have positive 294.3 because you move those to the other side. Equation 3, RZ's, we have 1. T's, we have negative 0.233. No constants. Equation 4, MX's, we have 1. T's, we have 0.070. Constants, we have 73.575. Equation 5, MY's, we have 1. T's, we have 0.466. And equation 6, T's, we have 0.279. Constants, we have positive 147.15. I got that the R vector is equal to 491.0, 147.2. I'll just write these quietly, sorry. Anybody have answers yet? Same thing? Yeah. Woo! I had a statics class once and we did this problem and like say we had 5 boys working on it and 5 girls working on it. And all of the boys got the same answer and all of the girls got the same different answer. It was like the most amazing thing I'd ever seen. Because apparently the 2 places on the board where I wrote it, like I'd written the answers. And so like all the girls looked at one spot and all the boys, very weird. It seems like somewhere in there was like a psychology PhD project, you know. Okay, so what can we say about this? One thing we can say is, okay, so what's your strength to create a couple with like a screwdriver? I think I mentioned this once before. Like, what's a ballpark of what? 10, right. So about 10 Newton meters, that's about how much you can apply. So this is 25 times, a couple 25 times as big as you can apply with your hand. I didn't give any specifics about how this joint was built, but that's a concern. We're asking like a hinge on the wall here to apply a couple of, 246. And of course, so there's a good chance that couple is going to damage that hinge. We would be better off, instead of relying on a single hinge to prevent that rotation, by having two of these hinges sharing that same axis to provide that. So now, I don't know how far we're going to get into this, but we can at least do the free body diagrams and stuff and start the problem. Yes? Well, okay, so if that joint wasn't there, this thing would accelerate. So it wouldn't be in static equilibrium. That joint's there to keep it in static equilibrium. But in order to stay in static equilibrium, that's the couple it has to apply. Okay. And so that's just a big couple to expect this joint to withstand hour after hour, day after day, if this is, some engineering application.
Intuitively, I'm thinking that having the two does more than just share the load between the doors.
Yeah, well, what it does is, remember that it makes it so neither of them have to apply any couple at all. All they have to apply is forces, because remember that equal and opposite forces are what create a couple. And so now these things are acting at a distance from each other, can provide that couple without doing it themselves internally. Okay, so, let's do the next one. So here's the plate. And I don't know if I said which one has thrust and which doesn't. Let's say that we'll keep the thrust over here.
So do you always just tell us whether or not it has thrust?
Yeah. Okay, so this one has thrust. So we're going to have 3 components of force. And I'll call that R1. But since there's another hinge, another pin joint sharing that same axis of rotation, we're not going to put any couples in this. So now I'm just going to go to this second one. And it doesn't have thrust, so it's not going to have a force component along the axis. It's just going to have the other 2 force components. So I'll call this will be like my R2X and my R2Y. There's no R2Z.
Like, we're assuming all the thrust is on one pin,
Right.
one joint. If you didn't break it, wouldn't it be evenly split between the two?
Yeah. Yes. This is just for our calculations, really. The thing is, we wouldn't be able to know how much has one and how much has the other. So at the end, you'll get a certain amount of thrust force. You could just roughly assume they're going to be split up between the two, if you use the same joint on both of them. But so really, technically, if they both provide thrust, it's statically indeterminate is the problem. So this is a quick workaround. Okay, so this is 294.3. And then We have the cable force T, and that's it. And now we're going to go to the table. We can skip a little bit of the work that we did last time because we already did it, and it'll be the same. I'm going to choose my about point over here again. So R1 has 0 row vector, R1x, R1y, R1z. Moment is 0. Then R2, the row vector is in the negative z direction, 0.5, so 0, 0, 0.5. The force is R2x, R2y, 0. Yes, thank you. Yep. So for x, we have 0.5 R2y. For y, we have negative 0.5 R2x. And then for z, 0. And then for the weight, the row vector is 0.50, negative 0.25. The force is 0, negative 294.30. For x, we have negative 73.575. Well, these are all going to be the same as they were above. Negative 147.15. And then the last one is t. And we can skip all that work. We have 1, 0, negative 0.25. Negative 0.25. And then negative 931. Positive 279. And negative 0.233. And 0.0704662. 0.070 T, 0.466 T, 0.279 T. And were those all positive? Yes. Okay, so I'm just going to jump right into this table. Sometimes that's a bad idea. We'll see how it goes. So these are equations 1, 2, 3, 4, 5, 6. And then we have R1X, R1Y, R1Z, R2X, R2Z, T, and the constants. Equation 1 is the x's for the forces. So R1x, we have 1. R2x, we have 1. T, we have negative 0.931. Equation 2 is the y's from the forces. So R1y, we have 1. R2y, this one should have been y, not z. Okay, so R1y, we have 1. R2y, we have 1. T, we have 0.279. And the constant is positive 294.3. Equation 3, R1z, we have 1. T, we have negative 0.233. Equation 4 are the x's for the moments. So R2y, we have 0.5. T's, we have 0.070. And the constants, we have positive 73.575. Equation 5. So R2x, we have negative 0.5. T's, we have 0.466. And no constants. And then equation 6, we have T 0.279. Constant is 147.15. And okay, anyone have answers? Same? Yes. So in this case, by putting in 2 of these pin joints along the same axis, we were able to do this without requiring any couples from either of those 2 joints. You can see the forces change a little bit. The magnitude doesn't really change. The tension is exactly the same. And so, if you're designing, that's why you never see doors that just have a single hinge on them, because requiring the door to produce those necessary couples, all it's going to do is break that single hinge, Okay. We're going to have a quiz on Monday. Okay? Just a quiz at the end. It's not a big deal, but we are going to have one. Okay, goodbye. Have a good weekend.